Google Docs. And you probably played games that sync with the cloud for high scores, to get new content, and most important, to show you ads. But making these applications scalable and reliable is difficult. So while not all tweets, for example, my tweets just get retweeted once or twice, you get a couple replies on them, some people are far more popular. So this tweet by Ellen DeGeneres was retweeted a record number of times, and that caused Twitter to almost come crashing to a halt. So we have to be really ready to deal with those skewed distributions. We also need to be ready for unexpected load, for sudden traffic spikes, for adverse network conditions that might affect our applications, like when the Star Wars tickets went on pre-sale and almost crashed a bunch of ticketing websites. And of course, no talk right now is complete without a mention of Pokemon Go and how it's so popular that every time everyone gets off of work, starts playing Pokemon Go, it's assuming they're playing less during work hours. It brings a bunch of the servers crashing down because they just don't have enough servers to handle all that load. Luckily, I'm here to help, and all the programming models that we've built in this thesis can help use types to communicate application semantics to make it easier to build these distributed applications so they themselves can optimize performance and make trade-offs for you. So before we get into all the systems that we built and new programming models, which I'll tell you about later, first I want to give you a bit of an introduction to distributed applications and some of these fundamental trade-offs that people who are building these applications have to deal with. So we'll go back to the Star Wars ticket sales app. So we want to build one called Ticket Sleuth, which is way better than Fandango and doesn't crash like it. Actually, I don't think it was Fandango that crashed, but don't worry about that. If we're going to build this application, we're probably going to have our mobile application talk to some server in the cloud somewhere that's going to be able to look up movie times, track the number of tickets that are remaining for each movie, save all the other information that you've saved somehow into a database. But what happens when we have lots of users so it's too much for one machine to hold all that data and manage all the traffic? Well, one thing we can do is we can shard our data store over multiple machines. Now, each machine is responsible for a subset of the requests. Now, if we have anything that needs to access data that end up getting split over to more than one machine, we're going to have to do a bunch of extra communication to make sure that that all ends up in one place so we can work with it, right? So this leads to a fundamental trade-off. The more we shard our data, the more we can scale, but the more we have to worry about locality of data. Right? Another thing that we have to worry about in these applications is what happens if one of these machines goes down, or if we lose network connection to that machine temporarily, or something like that. So what we usually do to get fault tolerance and availability is we replicate all of these shards in multiple data centers. Now clients can talk to any one of the replicas to get their data, and we can even distribute these replicas around the world so that no matter where the clients are, they can always access one that's close by. Right? But what if one of these users tries to make changes to one of these shards? Now we have to keep all these different replicas in sync with each other. So this leads to another fundamental trade-off between replication. So the more you replicate, the harder it is to keep all the replicas in sync with each other. Now, this already seems pretty hard to manage. You got these two different axes, performance you have to deal with, and there's no perfect solution for any of these. But actually, it's way more complicated than this diagram, than even that I've shown on here. Applications are usually split between your mobile client and maybe some application logic and servers. And then the system that you're using to store all that data is usually a complex ecosystem of databases, caches, other services that call out to ticketing websites, things like that. And so really, if you're the application designer, all you can do is use the interface that's provided to you in order to shape the way this system performs. Right? And so we have to think about what is the interface that we use to program these big, complicated distributed systems. And unfortunately, what we have usually right now is pretty simple, low-level things that I'm going to characterize by just saying they're like a big key value store. It just lets you do simple, low-level operations, like a put of a key with a certain value to store some data, or a get by a key to get some of that data back out, right? Really low level, not much information about what's going on. So the problem is that now we have the system that doesn't know much about the structure of the data, doesn't know what it should put in the same shard as we access together, doesn't know how the application is going to behave or what kinds of things, what kind of operations are going to happen together a lot. What we need is to be able to provide some more of this information and restrict how we use that data. Luckily, we have these things we call types, which we use all over in computer science, right? And you've all learned these many times, but I'm just going to talk about a couple different cases in CS about how we use types to restrict how data is used. So first of all, we use abstract data types. So one of the first things you learn when you're in the intro classes. Georgia, you can sit right here next to Mark. I'm just kidding, you don't have to sit there. Sounds like a terrible seat. So abstract data types, or ADTs, let us express high-level behavior about the data structure and hide all the low-level details that are used to implement those data structures. Type annotations let you provide a little bit of extra orthogonal information about data structures that you wouldn't have had otherwise. And type systems are used in programming languages everywhere to restrict how you're able to use data so that it can statically prevent you from making mistakes. Certain mistakes, not all mistakes, until a constantine finishes. Those dependent types. All right, so the thesis of this work is that we should be able to design new interfaces between applications and distributed systems that use types to communicate more information about application semantics to the distributed systems. Then we can build these systems to take advantage of those semantics to make these trade-offs for us and improve the performance of applications. So I'm going to start, I'm going to tell you about all of the different programming models that I did in the work in this thesis. I'm going to focus most of our time on this first one, on IPA, and how we use that to trade off consistency. But then we'll talk about the other ones briefly near the end. So first, a little more background on consistency. I'm going to tell you about how and why we might actually want to trade off consistency between strong and weak, and then what kinds of bugs can come about when we do switch between weak and strong consistency. So we use these things called consistency models to reason about the order that operations execute on data and the way that they become visible to each other. Just to head off any people who want to start fighting about what consistency means, I see you there, Irene. I'm just going to use a simple definition here that is just talking about replicated data and different gradations of consistency there. We're not going to talk about how database people think of it, things like that. All right, so the weakest consistency model that people typically use is called eventual consistency. The only guarantee here is that if you stop making updates, eventually all the replicas will agree on the same state. So let's say we have a counter initialized to 100 on all three of our replicas here. If a client decrements one of these counts to 99, then what's going to happen is those updates, those changes of -1 are going to propagate to all the other replicas at some point, using a variety of protocols like anti-entropy and gossip, right? If another client reads from a different replica, it might get the old value, but this is totally fine and normal. This is fine because these two are concurrent. We don't know which one happened first, so it's okay for it to get the previous value. What's concerning is that with eventual consistency, the same client could later read the value after it decremented and see the previous value. It's because eventual consistency lets you read from other replicas, which may not have those updates yet. So this is concerning. You're not guaranteed to read your own writes in this model. But because you're allowed to talk to any replica, it's really fast, really tolerant to failures. If you lose any node, you can just go talk to a different one, no problem. Right? If you want to have something that's a little easier to reason about, you might go with some stronger form of consistency, where you can guarantee that you'll see the effect of writes after in subsequent reads. However, this requires that you look at how you synchronized both the writes and the reads in order to tell what consistency you actually observe. Right? So what it means is you have to look at the number of replicas that you synchronized your write with, plus the number that you synchronized your reads with to make sure that they actually will see that write. So let's take a look at an example here and make sure that total number is greater than the number of replicas. So if we have 3 replicas and we wrote to 2 of them, and then we read from only 1, we might get unlucky and pick that one that doesn't have that write, and then we wouldn't see the update. If we want to guarantee that we're going to see that update, we have to read from at least 2 here to ensure that one of those is going to overlap, or to make sure that the read and write sets intersect. It doesn't have to be symmetrical like this. We can also choose to write to all 3, synchronize with all 3, and then read from any one of them, and we would know that we would see that right. Strong consistency like this is much easier to reason about. Now you will see things happen just like you were used to in your programs, but it's typically much slower. In our experience, it's 2 to 10 times slower. And that's because it's highly dependent on network latencies, or any one of the replicas could really seriously slow you down. There's actually a whole zoo of different consistency models that span this huge gap between strong and weak consistency. You have linearizable, that is really strong and serializable. You also have things, as you move down this spectrum, you get weaker and weaker ordering constraints, right? But you get better and better performance. Yeah.
Is the left side of this thing a regional contribution? Or
no? Most of these other people have thought of.
Okay.
The serializable has shown up in Twitter once or twice, thanks to Sam. So, yeah. Monorail, I came up with.
That's nice because it eats all the performance. Or?
Well, it's also the leader of the pack.
Oh right, yeah. Okay. So
back to our ticket sleep now. Most data stores let you trade off and choose different consistency levels for each operation in your application. So we're gonna have to choose when we build our ticket sleep application what consistency level we want, right? So let's say that we're gonna allow people to browse all the movie showings for Star Trek here. See, I modernized this because Star Trek just came out. So I'm not talking about Star Wars anymore. All right. So what we do is we have we let them view different listings, and then for each of these we keep track of the number of tickets that are left for that, and we show them an estimate of the number of tickets. So we have a ticket count initialized to 100 for each of the movies, or however many there are, and then obviously we allow them to purchase the tickets at some point. When they purchase a ticket, what we're going to do is decrement the count to reserve that ticket for them. And we have to make sure that this count doesn't go below 0. I'm simplifying how you actually purchase these to make it easier for these examples. It's obviously much more complicated. Right? Now, the important thing to note is that if we're loading a lot of ticket counts as you're browsing, you don't want to slow that down by doing all of those reads of the ticket counts consistently. So maybe you choose to use weak consistency to load those. You're okay if the count is a little wrong, it's not a big deal, they're still gonna have to go through the other process to buy the ticket, right? But when we go and buy the ticket, we don't wanna use that weak ticket count when we're trying to compute whether or not we can buy a ticket. We might not even wanna use that when we're telling them in this other page how many tickets are left, because they might not know if they should click fast or not, right? In general, changing consistency like this within your application is actually really unsafe. You could very easily end up using one of these weak reads in the wrong place in your application. And it's just not the right way to optimize it. We were trying to meet some higher level application requirements by changing the consistency here. So let's think about what those requirements actually are. We've got some hard constraints. We don't want to lose any user data or sell too many tickets. We don't want to charge users twice. So these are like strong consistency constraints. We also have performance targets in mind. Like we wanted our browsing to be fast and responsive and respond in, say, less than 50 milliseconds, no matter how much traffic there is on our site. All right? And then we also probably have in mind some of the things that we're okay with being a little bit incorrect. Right? So we have some idea of we can tolerate error in the counts on the browse page because so maybe we're okay with it being 5% off, but not like an order of magnitude off, right? So we have some idea of how much error we can actually tolerate in these applications. So the IPA, or inconsistent performance bound approximate programming model, is used to let you express these application requirements about consistency and performance and error tolerance in the form of type annotations and consistency types. And then the system is going to use those to enforce consistency safety using a static type system. And it's going to dynamically be able to adjust its consistency in order to be able to meet all those requirements for us. So I'm going to tell you first about the programming model, and then we'll get into how we enforce those constraints and dynamically adjust consistency. So generally, everything in a data store is going to return a value of some type. Right? So if you read the value of a counter, you're going to get back an int, usually, say the int 99. In IPA, you get every value that's returned from the data store is tagged with a certain consistency type. So in this case, this was a consistent, a strongly consistent read. Then we're going to get back a value tagged as consistent. So it's a consistent int. Now, the square brackets are the scaleless index for type parameters. Right? So this is a consistent int. That's how we expect values to usually be when we read them. And so we actually allow these consistent ints to be treated just like normal ints. So there's an implicit conversion to the underlying data type. This way you could just use it in your program as if it were an int. On the other hand, weak reads, say reads using eventual consistency, are going to be tagged as inconsistent. This will prevent us from using them where we might have accidentally used them. So if you did a weak read from the stick account, you're going to get back an inconsistent int of value 99. Or if you read from a different replica, you might get the value 100, right? And you don't know which one you're going to get. So in order to help us track that uncertainty, we tag them. And now, in order to get the value out, you have to explicitly endorse it, either using the endorse or using a case match to extract the value out. Right? But now you're prevented from accidentally using these values in the wrong place. Now, the consistency types actually are partially ordered, and they form a lattice, where the strongest at the top of the lattice is consistent, which we said you could convert to the underlying type. That means you know exactly what the value is supposed to be. Everything lower in the lattice is going to be progressively weaker until you get to the bottom element, inconsistent, where you know nothing about it. Right? We have a bunch of other types then that are in between those. You have intermediate consistency levels that are supported by your data store, such as local quorum, which Cassandra supports, which lets you say that it's consistent within one data center but not globally. And then we have these other ones, which we'll get to later, that are dynamic consistency types that have to do with how we dynamically adjust consistency. Right? So in general, what we try to do with this type system is we prevent weak values from flowing up into stronger computations. Right? So we prevent that flow from weak to strong. So let's just show you an example of that. If you got back a value that was inconsistent, the value n here, and then you tried to use it in a comparison against a consistent value of 100, you'd get a type error, a compile time error saying you can't use an inconsistent value as an integer, as a consistent value. Right? So then you will not be able to make those kinds of mistakes. You can, of course, endorse it here, but then if anything goes wrong, it's your fault. It's not our fault anymore, because we warned you. All right? Now, every item in the data store has a data type associated with it, and that data type has a number of methods on it. You can think of these as ADTs. So if we have a counter, it might have methods such as increment, decrement, which both return nothing, so that's the return unit. And there's a read to get the current value of the counter, which returns an int. Right? So now we're going to be annotating these data types with consistency constraints to specify how consistent the results need to be. The consistency constraints to use then determine the consistency type of each of the returned values from these methods. So if you annotate a counter with strong consistency, then you're going to get the reads returning consistent ints. Right? Also, if you annotate it with weak consistency, you're going to get back inconsistent ints. Okay? These static consistency constraints correspond to levels that are supported by your data store. And the implementations of these data types just use the data store to enforce, say, strong consistency that we talked about before. right? But these are not really a whole lot more interesting than what we had before. We just now have wrapped them up in data types, and we can catch consistency bugs, but we still can't specify application requirements, like we said. And that's where dynamic consistency types come in. So we have two different kinds of dynamic consistency constraints that you can apply to ADTs, and I'll tell you about both of them. We'll start with latency bounds, which lets you set a performance bound on your values. So the idea behind latency bounds is that you need the result of your reads in a certain fixed amount of time, and you're okay having the system dynamically adjust the consistency in order to meet that, that time limit. Right? So what we would do is we allocate a counter with a latency bound, say, of 50 milliseconds. That means that the reads are going to be expected to return in less than 50 milliseconds. Right? But now we might have a bunch of different consistency levels being returned, so we have to represent those somehow. We use a type called a rushed type. This could hold any of the different consistency levels. At runtime, we have to check to see which one we get.
Friend,
yeah.
In practice, how do you think a programmer chooses that number?
It's a great question. So usually services like Twitter will have service level agreements that they've made with like their customers about how quickly they have to be able to respond. So they have a certain latency for a certain percentile of the responses need to be in that time. So that would maybe say everyone's going to respond in 100 milliseconds. Then you as a developer are going to have to chunk that up and figure out how much we can afford to spend on this particular part of the application. If we consider this abstracting like the whole data store, then at least it's, this is specifying at the level of like the entire data store, this is how much time we are giving it to respond. But it depends on how deep your chain of dependencies is in order to determine kind of what you set it there.
All right, that seems very challenging.
Yeah.
For a real application to pick a number.
Yeah, I mean, it's strictly better than not being able to set a time bound. So the problem is that there's not a really easy way to specify those. So, there's not one piece of code anywhere that has like that entire chain. So usually these are a bunch of different applications that are running in a bunch of different servers, all talking to each other. We don't really have a good abstraction yet for how to tie all those disparate services together so that you can actually specify end-to-end latency constraints. There might be some work that does that.
But how about when you're doing synchronization operations, when you know how long you want to keep a certain lock, for example, to guarantee system level concurrency, then you should be able to infer the number from that, right?
Yeah, it's still not end-to-end though. Mark's asking.
It's not end-to-end, but yeah.
Yeah. So
how
the
do
end-to-end
you know?
problem is definitely really hard, and I don't have any great solutions to that besides do this but more.
And how do you know when you can't guarantee any bound?
How do you know when you can't guarantee a bound? What do you mean?
Right. Like when you can't
yeah.
guarantee anything, like
Right.
even that we do get back. So how do you?
Yeah. So the semantics have to be defined for latency bounds. What we
Right.
define them as is that we decided that we didn't want to just return nothing to you in that time limit because that's useless to you, right? Mm-hmm. So what we decided was to return a value at whatever the weakest possible value is that we can get the quickest. We'll return that, even if it takes longer than the time bound. So this is not actually guaranteeing that you'll have all your responses fast enough. And we'll see in the experimental results that they actually do exceed the time limit sometimes.
Mm-hmm.
Yeah.
So I still don't know if I agree that it's better than not having this,
Oh, okay.
right? Because now suppose there's like millions of lines of code that have been written in this, and they're spread all over the internet, and they have these numbers everywhere.
Yeah.
And then the back end changes somewhere, and things are changing, things are getting faster, some things are
Right.
slower.
And those don't make
How do
sense.
you even, what would you do to
Well,
fix that code? Wouldn't you rather just have all that kind of information somewhere else?
I would love to have it somewhere else. I would love to factor that out. So that's certainly a thing that you could imagine trying to do in a design that would look at the end-to-end performance, right? The problem is what you're saying doesn't exist either, right? So there's not a way to specify like those end-to-end performance requirements. The alternative to using something like this, as far as like this work is concerned, is that you would, so the baseline that we're talking about so far is you just pick weak or strong. That's even more dependent on changes in the system than specifying a time. right? That would be dependent, like whether you should do weak or strong is dependent on second by second changes in the traffic, right? This at least means you would only have to recheck these every time you change something fundamental about your system or until the workload changes somehow, right? There's certainly still gonna be cases where like something downstream has changed and now all those requests take longer and you have less budget.
You could ask the service for some time constants that make sense for it and give them names. And then if the service changes, you could send different time constants.
Yeah, that's a good idea. I guess like I don't know what you would, how you would try to specify that in the end then. But
Fast, slow, medium.
yeah. So that's actually a really great point that you could have something else setting these for you. You know, they don't have to be statically set. These are actually runtime constants. So what you could do, so the important thing about these is actually the second part. So rushed types, so when you have a latency bound and you're going to be adjusting consistency, you have to make the program handle all the different possible consistency levels that are possible now, right? And that's what the rushed types let you do. So rushed is a union type, so it has all those different types contained in it. And now it's up to you as the programmer to choose what to do if it's consistent or inconsistent. So once you've done that, then you could have anyone set those times for you, and you still have the benefit of having prepared your application for that. So the second half of it at least still helps you.
So this is like fast if you can.
Yeah.
But have you looked at
Or consistent if you can. Fast, as fast as possible.
right?
Yeah.
But have you looked at the flip of that where it's like you must be like a much harder bound on the result?
No, we haven't looked at that. First of all, I have no idea how I would do that on top of an existing system. So this is best effort, right?
Return zero.
Yeah. Oh, well, you could do that. I could change one line of code and do that. But I don't know what I would do with a non-value like that. So you could always wrap everything in like an option type, and then you could branch on whether or not it's some or none, right? And then you could do that. It just seems to make the whole thing more complicated when that seemed unlikely. Something that would be good to, you know, if we're going to do like a study with real programmers of how they would use this, maybe they want that or not. I don't, you know, this is something where I'm guessing based on seeing applications and talking to people that they can find that useful.
Do you have a sense of what programmers would do with this union type? Would they, you know, do something like a match like this, or would it just be always treat this thing as inconsistent?
I mean, you know, there's certainly nothing to stop you from doing that. There's no point in setting a latency bound if you're just going to register it as inconsistent.
I mean, at that point, it's exactly what you have now.
Right. So the what I saw in porting some of these applications was that it was helpful to know if a value was consistent, because then you know that your integrity constraints will hold. It's one of the things that's really tricky about eventually consistent data is that you may read one value here and you think that means that this other value is set, but it's not, right? That's an integrity constraint. And those may not hold if you have eventual consistency. So now what you have to do is everything you try, you have to wrap in a try catch or something saying, if this is null, then do this instead, which might require extra work, right? So it's not only like, it's not just that it's harder, it's also that it requires more computation time, right? If you get back a consistent result, you can skip all of that and you can just do the fast path, right? So this lets you write into your program that faster path for if you know that everything's consistent. You can keep doing that.
You could also use this if you wanted to have the system just degrade to something less fully featured if it's returning inconsistent values, which might be something you want to do anyway if this is happening when the system is overloaded.
That's a great idea. Yeah. So we'll see an example in a couple slides that one of the other things that it seems like you might want to do is warn users if it's inconsistent that it might be inconsistent. So one thing that will happen if you have an inconsistent value is that it may be that if you refreshed, it would work the next time, right? And you just got unlucky and like sent your request to Asia. And so like in that case, it would be better to refresh.
Maybe we should let you get to that.
Maybe we should get to that then. All right, so let's talk about how we implement these so that what I just said makes sense to you. So we can implement latency bounds, but first we have to think about what would we have to do to get a strong read. So we have to look at the number of replicas that we synchronized with to do our write, right? And that if we wrote to 2, then we know that our read, in order for it to be strong, has to read from 2 replicas in this case, right? So what we do is we send requests to the 2 replicas that we need for strong consistency. And then we wait for the specified time limit. So after we've gotten both these responses back, we can return after 30 milliseconds. But what we get is that the resulting consistency is determined by the number of responses you got within that time limit. So in this case, we got both of them back in less than 50 milliseconds. So we returned a consistent 99 value. If we got unlucky, which is what I was saying a second ago, and one of these requests took longer, say it went to our Asia replica instead, then we would only get back 1 response in 50 milliseconds. So we would have to return an inconsistent value. Right? So it all depends on how many responses you get back. That determines the consistency that you get. Yeah.
So instead of like waiting for a certain time, can I just have like a callback that I call whenever I receive something, and then like the user interface can update, remove more question marks as I get more?
Sure. You should talk to Irene about reactive programming models that you specify callbacks for when new data comes in. Yeah, actually, that's totally true. And in fact, the real implementation of these is all using futures, so that it all kind of works like a callback and does something whenever the response comes back. So it's all like kind of non-blocking code. But yeah, you could totally have something that would later update it again when the fully consistent result comes through. You may as well do that if you think that will help. Cool. So one problem that no one has complained about yet, well, there's a little bit about how we want to back off a bit, is sometimes these bounds are just completely unreasonable and you won't be able to meet them. So sometimes you might say 10 milliseconds right now is impossible because it's impossible to get strong consistency because only 1 replica is within 5 milliseconds away with network latencies, right? So what we want to do here is not waste all the extra messages trying to coordinate with everyone when it's just not going to be possible. So as an optimization, as an example of something you can do inside of the programming model without affecting the users at all, we can monitor latencies dynamically in the runtime, predict which one we think is actually going to be achievable, and just send messages for that. So here we could trim those other 2 synchronization messages and just send 1 to the closest replica instead, and just give up on trying to do strong consistency. Then later, if things subside, you can go back to trying to get strong consistency. So this can dynamically change over time. All right? So that was a hard performance bound if you didn't care about how wrong things were, right? But what if you know that you can't tolerate it being more than a certain amount incorrect? That's what error bounds are for. They let you specify a certain fixed amount of inaccuracy in terms of the actual value that you get back. So not in terms of how inconsistent it is, because inconsistency could return any possible old value, right? What we want to do here is bound that the values are within a certain range. So if you annotate a counter with a 10% error bound like this, then the reads are going to reflect a certain amount of uncertainty in what the value is. This reflects all the possible consistent, strongly consistent values that you could have gotten back from this read. Right? So this interval that you get back from a read now represents the range of possible strongly consistent values, and then you can choose what to do with that. So if you want to use the minimum value in that interval to be conservative, it's up to the program to kind of choose what it does with that interval value now. But again, you can't use it as just an int, so you will prevent yourself from accidentally using it in a way you weren't supposed to. All right? What's important to note about these is that they require you to know the semantics of operations on your data types. So a decrement operation will change the value by 1, right? So if you have 0 to 10 decrements in flight, then you know that the interval is going to be 10 wide, right? So we're going to have to, this is why these annotations have to happen on the ADT, not on individual operations. So how do we implement this without making it just as strong, as slow as strong consistency? Well, we limit the number of outstanding write operations that we allow. Right? We do this using a technique called reservations, which allow you to basically pre-allocate permission to do updates. And then, so in this case, if we had a counter that's a 100, and we wanted to enforce a 10% error bound, we could have 10 decrements in flight and not have the value change by more than 10%, right? So we then distribute these reservations among all the replicas. Now, if a client wants to do a decrement, it can just coordinate with a single replica, consume one of those reservations, and do its decrement locally without any other synchronization with anyone else. Right? Then, if another client tries to read from a different replica, it's going to get back an interval, right? Representing the fact that we don't know if these other nodes have done any decrements. So we don't know what the real value is. So in this case, it's going to return an interval that starts at the value it knows it is, and it thinks there could be at least 10, except it knows that there are 4 locally it hasn't used. So the interval ends up being 6 less than 100. So now it knows that the value is between 94 and 100. It doesn't know exactly what it is, but it returns that to the client. Okay. We get these permissions back whenever we synchronize with the other clients. So once these other replicas have synchronized with each other, then the reservation comes back, and we're back to the ones we started with. Also, every time the value changes, we're going to have to reevaluate how many tokens we have, because obviously if it's 99, we now only get 9 reservations. Right? In case anyone's worried about the fact that I didn't change that. And in fact, the data store that we used, Cassandra, doesn't support reservations. We had to build these in. So we built a separate set of reservation servers that sit next to the Cassandra servers and mediate all the requests to error-bound values. So let me show you how we use these different kinds of IPA types in our ticket sleuth application. So in order to keep track of the number of all the events, we have maybe a list of event IDs. We said we wanted browsing to be fast, so we can specify, say, a latency bound. That means that we'll get back from our reads a rushed value, which might be inconsistent. So then if we want to use that, we're going to have to endorse it explicitly. And if we notice that it's inconsistent, we might want to do something like display to the user a warning, or retry, or dial back some of our features because we know that the system is heavily loaded. Okay. Then we actually don't, for the actual ticket counts, we use a slightly smarter abstract data type than a counter. We use an ID pool data type. This lets us take a fixed number of unique identifiers from the pool, and it guarantees that it won't give out more than the number in the pool, even though it's distributed. It's actually a form of convergent replicated data type, CRDT, which I won't have time to explain. Right? But that means that when you take a value from this, it's going to be a consistent identifier. It actually is an option type, but don't worry about that. The count, then, we said we wanted the counts to be relatively close, so we could annotate it with an error bound of 5%. And now we're going to get back an interval saying the range of counts that are possible. And then maybe we choose here to use the maximum value so that we can show them the upper bound on how many tickets might be left. All right? So we evaluated this by measuring the average latency of responses under a simulated, heavily loaded system. Right? So when we try to use all strong consistency, we see that the latency is really high. It's 100 milliseconds on average. Note that this is a log scale, which is important because then when we look at what we get if we do all weak consistency, we get latencies around 5 milliseconds. Right? And as you might expect, ours is almost as good as the weak consistency, which is fantastic. Except that instead of arbitrary errors, we now can guarantee that it will have less than a 5% error on those remaining counts.
Yeah, you evaluate what the error actually the weak consistency get?
Mm-hmm. Yeah, so there was a different experiment. I don't have slides for that. But we did another experiment where we measured the actual error in the counter. And it's actually really hard to measure without perturbing the measurement, right? Because it's hard to tell what the actual count is in a distributed system. So in this artificially constructed setup, we saw errors up to 60%, but that's like the maximum. Usually they were around 1% in this workload. But obviously it's going to be highly dependent on the workloads and on the latencies and on the actual load on the servers. So it's really, you have to take that with a grain of salt. All right? So we simulated a bunch of different adverse network conditions so that we could see if it would affect it if there was one slow replica or if we had high latencies if it was distributed. But then we validated all of those simulated ones on actually distributed system. We ran experiments on Google Compute Engine, ran servers in Asia and Europe and both coasts of the US. And we saw that we got the same trends overall. Obviously, the latencies are going to be higher in general because we're sending requests around the world. But in general, IPA is able to perform as well as the weak consistency. And that's because those reservations allow us most of the time to use weak consistency to do bounded consistent updates. All right, so that was IPA. That was the longest segment of this talk.
Can you selectively go back to strongly consistent if you desire it?
Like at runtime?
Yeah.
No.
So once you have an IPA type, it just it is what it is. You can't
So well, what you're talking about is similar to what Constantine was actually mentioning earlier, where what if you wanted to like wait a little bit longer and get the consistent value but update it again, right? So with the stuff that we built, that's not a feature, but it would be totally possible for you to like have another thread that could execute a callback that would happen when you get the fully consistent value when all the responses come in, and change something asynchronously later. Would that do what you want, or?
Well, I'm thinking of token coherence. You remember this from Milo's thesis?
Yeah, a long time ago.
Yeah. So what if you just grabbed all the reservations?
Oh, well, that's something else that goes on. I went into a bunch of details of the reservation implementation. If you want to do something that violates the error bounds, if you want to update it by more than 10%, like initialize it, you do that by forcing everyone to synchronize and make sure that no one else is able to use any of those tokens in the meantime. So there's this other process that allows us to synchronize heavier weight things in order to do things that would violate those other constraints. So basically, you lock everyone from doing their reserved updates, do the bigger update, and then allow the reservations to go again.
By the way, there's a paper coming out in OSDI this year that's about exactly how the programming model you described, where you get the update with the strongly consistent value later.
Cool. Cool. Who's that by? Can you say? No, it's public information now.
It's not public information, but I don't know, so I can't say.
All right. Thought I'd try. I'm just curious if it's.
I want to say it's from EPFL.
The latency bounds are really heavily influenced by Doug Terry's work. So that's interesting.
It's more like promises that can be updated, basically.
Cool. See.
So there's a large list of systems where, because those kind of failures like double cell, so a lot of like systems like bio or down, or like even airlines, like the way they deal with double cell is constantly later, right? Give you some like it's okay.
Oh yeah, right. Like when Irene gets double packages.
To get free return, you get some credits. So how do you think your language runtime could be extended, or how to incorporate those in your
Yeah, that's a good idea. I mean, you basically, you can always just turn it off and use weak consistency if you're okay with making those mitigation techniques later.
They are weak consistency. The question is, how do you do this issue later?
Yeah, I don't know. That doesn't really fit into the model here, because the model here is that we're trying to. I mean, it's an interesting idea. I can't think of any direct ways that I would do it, except these kind of callback things, where if you later find that the value you showed someone is different than what you initially responded to them, basically same as this promises thing, you could have another, compensation like path that would happen when the strongly consistent value comes back and is different noticeably. You could have a threshold similar to the error bound threshold that would say, this is too wrong, now we're gonna have to fix it for them. So if it was less than 5% off, maybe we say, that's fine, they won't know the difference, but if it's significantly off, or if they bought the ticket already, then you could have that. So just keep track of the value you showed them after the initial latency boundaries fail, and update it with the new value.
What I mean is, our infrastructure is built in a way that it doesn't require like full precision, right?
Mm-hmm.
Like the tickets thing charges your credit card.
Yeah.
But it doesn't matter because you can always cancel the transaction later. that seems fine, but it looks like your system needs to deal with this canceling transaction, that's all.
Oh yeah, these aren't transactions. So this was simplifying the problem down to just individual operations. And in fact, the ticket purchasing one, I said I oversimplified that example because really all I meant to do, all we're doing with this data store is reserving a ticket. So it's only going to give you a ticket if you can, and then if you decide to return that ticket, if you cancel your transaction, it'll put it back into the pool. But like I said, the CRDT actually can guarantee that you won't give out too many tickets. So like there are pretty clever ways of preventing those kinds of failure cases too. All right, you guys want to hear about some other systems? All right, so I will try to move through these quickly. There's a lot less detail on each of these, but there are different ways that we use types in some of these other systems to improve performance. So the next two are, rather than weakening consistency, which we did in IPA, we're actually going to keep it appearing to be as consistent as it was. We're going to keep it appearing linearizable, but we're going to use our knowledge about concurrency of abstract data type operations to improve their performance. So the first one is distributed combining. Here we're going to use associativity of ADT operations to improve the performance of linearizable shared global data structures. So linearizability is this property of data structures that enforces that all the operations on this data structure appear to execute in some global total order that everyone agrees on. So if you have two threads, the easiest way to enforce linearizability of their updates to this shared concurrent set is to have them both acquire a lock and then do their they acquire the lock, do their operation, release the lock, right? Unfortunately, if you have lots and lots of threads, this leads to really intense lock contention, which will slow down your program immensely. Luckily, we have really clever lock-free data structures that will reduce some of that contention. But the problem is that they still have to enforce a total order on all the operations. So everything is going to have to execute one after another on some thread that's responsible for it, probably, right? So it's still enforcing a global total order, which, as anyone who's inputted parallel applications knows, is doing it wrong, right? If you have all these threads and they're all doing things one at a time, then you're doing it wrong. So combining is instead going to get you to have the threads cooperate with each other and merge the operations so that we have fewer operations that have to synchronize on the shared concurrent data structure. So in this example, the two adds of these two people's names, Arthur and Zephod, can be merged because they're associative, right? So now they can be merged into a new set, and then we can just add that set to the concurrent set. And we can do that in a hierarchical fashion with lots and lots more threads to drastically reduce the number of times you have to synchronize with that shared data structure. Right? This has been done in a whole bunch of other systems since the 80s, using much different data structures for shared memory systems. What we did was we applied it to distributed systems where it's an even bigger problem. So let's say you have a cluster of machines and you want to build a linearizable global data structure like a stack. You might have a lock, and then you have all of the different threads that are trying to update that, try to acquire that lock, and do their operation, right? You can tell this is going to do really, really poorly, right? So combining comes to the rescue, and rather than having these cores do a really expensive remote synchronization, they instead synchronize locally with each other with these local combiner objects, and then each of the combiners can just do one operation for all of those threads, right? So this will drastically reduce the number of updates to the shared data structure to be roughly equivalent to the number of nodes, and now it's going to scale a whole lot better. So we did some experiments. I'm just going to show you a couple of them on two applications.
Sorry.
Yeah.
Do you think you could make a strong statement about combiners can be combined? Like for any given...
Combiners can be combined?
They're
not composable. You mean that?
Yeah. I think I mean composable. I don't know.
Yeah.
If you go back to the previous diagram, right? You want to have, for a very, very large system, it might make sense to have a combiner tree.
You mean hierarchical? Yeah.
Yes. So can you make a strong statement about for any given combiner, you can always apply a tree structure on top of it if needed?
Yeah, that is true. So combining is associative, right? And associative property says that you can associate it as many times as you want. Right? So as long as they're associative properties, as long as the operations are associative, then you can do that. It all comes back to using the abstract properties of ADTs. All right, so we did 2 evaluations on 2 different graph benchmarks. Right? Breadth first search is using a global queue, and if we implement it naively, we're going to get really low throughputs. This is showing throughput as we scale up the number of nodes. We see that that's almost completely flat for a naive implementation of a global queue. Right? But with combining, it scales almost linearly, not quite as well as a custom data structure that uses a little bit of extra asynchrony to get more performance. Right? And we see similar results with the components implementation that uses a global hash set, where combining does better, but not quite as well as the custom data structure. We can talk more about that if you guys want, but I would rather move on to the next system.
One question. So,
Yeah.
like, how, as a programmer, do I know when I can take my data structure and make a combiner version of my data structure?
Great question. So most of the time, you won't have to. So the idea is that whoever designed this library of global data structures for you, which is what I did for Grappa, will have done that work for you, and you just use them as if they were a normal data structure. So we haven't changed the semantics of the data structure at all. And that's what's great about the difference between the green and the yellow bars here. The yellow one requires you to know, so this one, using a custom data type, is changing the semantics of the data structure in order to make it perform better, right? Which actually requires you to think carefully about when that's feasible. The combining ones are without changing any semantics, just doing it smarter, you get almost the same performance.
So I have a general question. Actually applies to IP as well. So why types? I understand that there's some benefits, but could you have gotten similar benefits with operation-centric specifications?
Yeah. So I said with IPA, there are specific reasons why data types are important because you have to pair, read, and write. Right here, the fact that those operations are associative is actually a property of the ADT itself. So those operations in isolation, we know nothing about them. Once we know that they are adds to a set, we know that they are commutative and associative. Right? So without that extra knowledge that ties the different operations together, we don't know that.
But you can tie them together with things other than types.
Yeah.
Right?
So the nice thing about this is that, and we'll get to this at the very end, you're already using these data types in your applications, right? If you're already using them, we may as well take advantage of that information. So the core idea of all the ADT stuff is you're already using lists and queues and sets in your applications. Why don't we take advantage of the semantics that you already know about inside the system?
Are there other things that are useful to use, like monotonic, constant?
Yeah, you're just naming properties that you pick up, right?
I just did my best here.
Yeah.
So how would I use a monotonic?
So yeah, I mean, so I don't know. If I had thought of a really easy one, it would have implemented it for Claire. And the paper would have gotten accepted. But so I mean, monotonicity is another really useful property, especially because it allows you to not have to know that some things might be removed, right? So a monotonic set would allow a bunch of different optimizations that you can't rely on if removes are allowed, right? So there's certainly a whole class of things that way. I don't know exactly what I would do. Probably the best idea that I've had on that respect is tied with phasing, which we can talk about once we get to the Claret stuff. But basically, if you knew you had a phase of monotonic changes, you could detect that and do optimizations based on that, and then wait and do all the removes later. Right?
You could use gin and tonic as well, right?
Yeah. Well, so I don't have all of the systems and all the alcohols have not been taken yet.
Right.
Yeah. All right. So let's just talk about a slightly different way of using abstract data type semantics in Claire. So here, in the last one we use associativity. Here we're going to use associativity because we'll have combining as well. But we're also going to use commutativity of operations in transactions. So in transactions, what we want to be able to do is detect whether multiple operations together are conflicting with each other. So let's take a look at a transaction for the the purchasing example here. So if we wanted to buy this ticket, again, oversimplifying the process, right? You read the value, see if we decremented it's still greater than 0, and then update the value, and then do some other stuff, right? The problem is if we have 2 transactions like this, to the transaction processing system, it thinks that these are conflicting because the 2 are reading and writing the same value. So the problem is that we're using this low-level interface of put and get operations, or read and write. Right? What we can do instead, and what Claret does, is it uses the higher-level version of those operations, which we talked about before. We said that the purchase operation is just taking from this ID pool data type. And this ADT, this pool ADT, knows that takes will commute. Right? So it actually is true that if you have lots and lots of tickets, you can take tickets in parallel, and there's no worry that either of them will go to 0, right? So those can be done in any order. So we don't have to enforce a linearizable history of these transactions. We can actually just run these 2 concurrently, and they don't have to cause any aborts, right? So that's what we do in Claret. So they commute as long as they don't run out. If one of them goes to 0, then they wouldn't commute anymore, right? So what I just was describing is called transaction boosting. Basically, you lift your representation of the transaction to ADTs, and now you can deal with commutativity. And we also added some optimizations that reorder operations within between different reorder transactions in order to have commutative operations go together in phases. And then we use combining as well. So I'm just going to show you one of the experiments that we did on a prototype data store implementing Claret. So I'm going to show you a micro benchmark that is doing transactions with random set operations. I'm going to show you, as we increase the number of clients, what happens to the throughput. So we see that the baseline that's just using dumb reader-writer locks can't scale. It peaks at 64 clients at 20K in transactions per second, and then just degrades from there. Just adding boosting gets you a bit of a boost, pardon the pun. But if you add phasing and combining on top of that, you end up with 2.5 times better throughput. Okay? Now, something to always consider is what is the cost of making these transactions. So if we ran that same workload and just didn't do it with transactions, just eliminated all the transactions, it would be wrong, but it would be much faster. And it would be about 33% faster. So we're taking a 33% performance penalty, but that's significantly better than the penalty we were seeing before from without transactions to adding this, which is an 87% degradation. So still significantly better. You might actually choose to have a correct application with this kind of performance slowdown. All right, and then the last system, which I think we're going to get to all of them, is called Alembic. So this, imagine you have a large graph. This is a gene co-expression network. You might try to learn a gene regulatory pattern. And this graph is really big. It's going to take a while to do the analysis. So you want to use a cluster to do it. You haven't talked to the people who say that you should use really big, fat machines with lots of memory. And so let's say you want to do that. You're going to split your graph over the whole, over the memories of all these different nodes. And that's what we built the Grappa runtime for, when I built along with Jacob and Brandon Myers, if he's there, and Preston and Simon, was this runtime that lets you treat a cluster like a big shared memory system. Basically what happens now is if you have a thread and you want to access data on another node, you go send a message to that node, fetch that data, and return it back to your thread. But this leads to a lot of round-trip messages. You got to wait for both of those round trips to come back. And if that data is really big, you might be moving a lot of data over the network. Sometimes it's actually better to move the thread to the data. So in this case, what we can do is just move the thread to where the data is. It works on that data, and then it moves on to the next one. Right? This is especially popular in some of the applications that we worked with. Right? The problem is in Grappa, you had to do this all manually. You had to choose when you wanted to migrate or when you wanted to fetch data remotely. So what Alembic does is it just has you annotate which pointers are to global data, and then it automatically figures out when it should migrate, when it should move computation, and when it should move data for you. So I'll just show you briefly how this works. You start with the C++ program like this that's using a pointer to increment a counter, and you just add the global type annotation on the pointer type. Right? This tells our analysis that these pointers are special, that they're going to go to remote data. It's going to have to generate droplet calls to get that data remotely. Right? Then we do a locality analysis on the dependence graph, figure out which points are to remote data, and then we try to figure out where we should migrate to minimize the communication. So we analyze those, figure out the minimal migrations that we have to do, and then we generate continuations to do that. Continuations just package up everything you need in the thread so that you can move a tiny amount of state, which is much smaller than trying to actually do a full thread migration. Right? And together, this actually does really well. So we implemented an LLVM on top of the Grappa runtime. And then we compared its performance on a bunch of different benchmarks we'd already built for Grappa, mostly graph analytics benchmarks. And we compared it with a naive version that just does all put and get operations, and then against a manually optimized one that does migrations that we chose to be optimal. Well, that were optimal, that we chose ourselves. And the throughput here is normalized to the put and get. So we can quickly see that with Alembic, we got 6.5 times better performance overall on these 4 benchmarks. And that was almost as good, within 25% of the throughput of the manually optimized versions. So those are all the systems that I had in the type-aware programming models for distributed applications. All of these are trading off application knowledge, or using application knowledge to improve the performance using system-level optimizations. So we've got the performance and accuracy requirements of IPA that are used to safely trade off consistency. We had Claret and combining that used commutativity and associativity of abstract data type operations to improve the performance of transactions and make linearizable data structures faster. And then we had Alembic, where we used type annotations on those pointers to communicate more information and minimize communication. So overall, this is what Luis was asking about. We're reusing types because they already exist there, and that makes it so that we don't add a whole lot of burden on our programmers. And this lets the systems make smarter trade-offs. They have just the right amount of information, not too much that they're specializing for each application, but not dumb put and get. And with that, I just want to say thank you to everyone in this room and to everyone on the picture here. You guys all made this way more fun and helped me with almost everything I said up here, so I apologize for not attributing each of your contributions. No one got to be consulted on which picture they just put up. So thank you to my mentors and advisors, Mark and Luis, and to Dan and Eric for being on my committee and advising me on stuff, from my co-authors, for all of the collaborators on different projects, for all the members of SAMPA, Pulse, SysLab, anyone else in UW who's here. And so yeah, everyone's covered. You're on there somewhere. And Pursu Ariel, who has helped me sample all the various alcohols that we have talked about here, and also, helps me have more fun. And yeah,
What about your parents?
They're I forgot to put them on this slide. They're definitely in the acknowledgments section. I apologize. I'll get a new draft of this with those corrections. And unless you guys want to keep looking at your own pictures, I'll just go to this where you can look at the various system icons. And you guys can ask me any more questions you want. But thank you, everyone.
Questions from non-committee members?
Were you just drinking wine?
That was cold brew coffee. So I talked so fast to get through all that in an hour. Yeah, if you want some, there's a little bit more. Any other questions?
All right, no,
Thanks for coming.
Oh, Luis has a
I
question.
have more questions.
Oh,
Well, it is going to be a closed
well,
session.
I mean,
No.
that's the
One
public
question.
Public
Go.
Okay. So the first one serious question, one last serious question. The first serious question is, so I want to talk a little bit about composability, right?
Oh,
so,
sure.
I mean, I understand that you get some guarantees if you compile everything together because your analysis has to include the entire source code. But the way we build distributed applications have a bunch of microservices interact with each other and so on. So how would you extend the guarantees that you have, beyond single executor, single code-based analysis?
So that's great. I mean, basically, there are a lot of techniques to try to get closer to whole program optimization in compiler and PL land, right? And basically, one of the things is expose a couple more properties about each of these modules to the systems they know about each other, right? So one of the things you can imagine doing is if all the components all exported like which ADT things they were using, which properties they were trying to optimize for, what the latency requirements they had were those kinds of things, then you could imagine taking this rather than use that interface that's more tied to the applications, but not like every single detail, right? So I actually think the ADT thing is again one of these nice kind of middle grounds where it's not too specialized to any particular application, but it can communicate a whole lot of information about the semantics and the behavior. And you just have to add those annotations of like the performance constraints and the correctness constraints to that specification of those modules.
So there are questions.
I don't know if Eric has a real question.
I have a real question.
Yeah.
So you're using, so your thesis is about using all these types, but it seems like you're also using runtime information to perform optimizations both like before execution and during execution. Can you say more about the trade-offs that you found between like information coming from the static information versus dynamic information and static versus dynamic optimization?
So that comes up in a lot of different places here. So like, for example, in Alembic, all the optimizations were static. So we assumed that it only worked because in Grappa we knew the static size of each of the data types we were using. Right? That would make it much harder to do those analyses with only static information if you have dynamically sized objects, like strings. Right? So that's a huge gap in that, which would require more runtime information, right? Similarly, most of the properties that IPA was optimizing for are basically trying to make it so that it's actually kind of the opposite direction. It's statically preventing things, but it's mostly forcing you to deal with all the dynamic runtime junk that's going to happen, right? So the idea is like all this extra runtime information is stuff that your application has to be ready to handle. So the runtime of a distributed system is way more variable and dependent on conditions than applications we're used to. So we have to design our programming models to expose that to programmers.
In which order should you drink your systems?
Beer before liquor, never been sicker. Is that how that goes? Or liquor
Actually,
before
that's a
beer,
somewhat
never been
serious
sicker?
question.
Phrased that way. Well, so yeah, this is hard liquor, right? And we assume. So we'll probably start with that, then go with a little wine, and then IPA. So in the order of when I completed that, in fact.
Okay, we'll ask more about
Mine is
that
program
later.
orders, but-
Yeah, but you don't have to drink grappa. That's not tasty. You can skip that one.
So what was surprising about your time in grad? What was the most surprising thing about your time in grad school for research?
How annoying it is to try to publish research, probably.
Wow, that's deep.
No one told me it was going to be hard to get things published. But I don't know. Also, how much fun it is. I mean,
And how not to be honest, right?
Yeah.
What's your favorite type?
My favorite type. Dependent types.
Cool.
No, I'm just kidding.
That's definitely not my favorite.
What type would you be?
Yeah. I think
Alright.
it's an independent kind.
All right. So thank the audience. Thanks the audience.
Yeah. Anyone wants to take any more pictures on the way out?